So, welcome to this new lecture of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we did in the last class. So, in the last class we did a treatment of ionic or electronic polarizability. The first treatment that we did, in that we found that ionic and electronic polarizabilities are temperature independent, and we also did not look at the frequency dependence. We just did it at the DC conditions. We saw that electronic polarizability is proportional to r cube, that is the size of ionic species, size of the atom, and then ionic polarizability was inversely proportional to the modulus. But then we took it a step further, and we did frequency dependence by applying a sinusoidally varying electric field and considering the electron cloud in the nucleus or the ions as connected through a spring in the form of a simple harmonic oscillator. As a result, we wrote the equation of motion, and then we solved it for a displacement x, and then based on that we calculated what is the what is the polarizability. So, polarizability was worked out as alpha I was qi square divided by m into omega oi square minus omega square plus I gamma I omega. This is what we worked out, and from this we can also work out what is the, so from this one can work out what is the polarization. So, this is alpha I star, of course it is a complex quantity. So, we can work out what is polarization. Polarization will be n alpha E, where n is the number of dipoles per unit volume, and then when you do the separation of real and imaginary part, and then we can relate polarization to susceptibility. Susceptibility can give rise to what is epsilon r, and we found expressions for epsilon r. So, epsilon r infinity was equal to 1 plus n into qi square divided by mi epsilon naught into omega oi square minus omega square divided by omega oi square minus omega square to the power 2 plus gamma square omega square, bracket closed, and sorry, this was the real part, okay, real, and then imaginary part was n into qi square divided by mi epsilon naught into gamma omega divided by omega oi square minus omega square to the power 2 plus gamma square omega square. Okay. So, this was the expression that we got, and basically this suggests that in the denominator you have this term omega oi minus omega square. So, the resonance will happen when your omega is equal to omega oi. So, your dielectric constant has to be measured at frequencies which are lower than this omega oi. The moment frequency is higher than the omega oi, the dipoles corresponding dipoles do not respond to the frequency. As a result, they do not contribute to the dielectric constant. So, when you plot these dielectric constants, so when you plot these epsilon r prime as a function of frequency, then we see something like that. So, this could be, so if it is for electronic, then this would be 1 and this would be epsilon r electronic, okay, and this frequency would be omega o e correspondingly, right, and at this point we will have the maxima in the epsilon r double prime, okay, and correspondingly if you plot tan delta, which is equal to epsilon r double prime by epsilon prime, you will see a peak in tan delta as well. So, basically what happens is that above this frequency omega OE, the dipoles are not able to keep pace with the frequency of the applied field. As a result, they do not respond. So, you have to go to frequencies below omega OE for electronic dipoles to respond. So, then only they will be able to contribute to the dielectric constant. Similarly, when you go below this for ionic, if I now make similar plot in the blue color as ionic, this frequency would be omega OI, and here it would be epsilon r electronic, and here it would be epsilon r ionic. Okay. So, this is how it will change as a function of frequency when you measure this dielectric constant. And another simple argument that one can look at is, see this vibrational frequency, basically this is a frequency, right. So, frequency can be written as omega naught can be written as square root of k divided by m, right. This is from classical mechanics. So, basically if you balance the force that is inducing the moment and the restoring force, you will get the value of a spring constant, and this omega naught works out to about, so if you just consider it as a simple harmonic oscillator with a certain value of k, then omega naught can be determined to be, so about 15 hertz for electronic polarization, and then about 13 hertz for ionic polarization. And that sort of makes sense because the mass of electrons is far lower than the mass of ions put together, right. So, as a result the frequency is down, and since this is square root, you can see that it must be about few orders of magnitude smaller. Okay. And another thing that you notice is that the frequency here for ionic polarization is about 13 hertz, which is similar to basically natural frequency for natural frequency of vibrations, right. Natural frequency of vibrations, lattice vibrations, is about so ions vibrating means lattice is vibrating, right. So, this is about 13 hertz for lattice vibration. So, basically this shows that whatever we have done is fairly right. And as you go to very high frequencies, naturally the dipoles do not respond. So, as a result epsilon r is equal to epsilon r infinity is equal to 1 at frequencies greater than 10^15 hertz, because none of the polarization mechanism is able to keep pace with the applied electric field. As a result, you have 0 contribution from them. All right. So, now essentially basically you can summarize this part as that for electronic polarization, omega critical frequency, the resonance frequency is omega O electronic. So, as long as your frequency is lower than this frequency, your dipoles will respond. And for ionic polarization, your frequency is lower than omega O I, which is lower than omega O electronic. Okay. So, and what this means is that your ionic dipoles will respond, and correspondingly at the resonance frequency we will see a maximum in the epsilon r, that is epsilon r double prime. So, at you will have a resonance and maxima in epsilon r double prime. Okay, so this is a very simple analysis for basically, let us say, this is a simple analysis for electronic and ionic polarization given their frequency dependence. And you can also convert these equations to find out what happens when omega is equal to 0. When omega is equal to 0, you should be able to convert them to similar DC equations that we worked out earlier. So, basically alpha electronic should reduce to 4 pi epsilon naught r cube. Okay. So, that is what it should happen. So, that I will leave it to you for working out. Now, let us look at the treatment of dipolar relaxation. So, basically frequency dependence of dipolar relaxation, and this is also called as often Debye relaxation in the name of Debye, and this is valid for mainly we can say polar solids and this could be variety of ceramics, dielectric ceramics, glasses and very many other systems. But so here we do not use that damped oscillator approach, rather we used a relaxation approach where some entity goes from one position to another position, relaxing from one to another. So here what we will say is that the movement of charges, the movement of a species, let us say, occurs over larger distances than as compared to electronic and ionic. So, it could be a few atomic distances, and as a result the phenomena is diffusional in nature. So, basically suppose you have a charged dipole like this, it was earlier in this fashion, now it has to move. So, this is the first position, now it has to move to this position. Okay. So, essentially it goes from this position to that position mu. So, all these atoms have to now hop from this position to, so this atom has to come from this position to this position, correspondingly this atom has to go from this position to that. So, everything has to rotate in a matrix, and this could mean the translation of atoms could be fairly large, of the order of atomic spacing or even higher. So, basically energetically speaking you can represent this process as the species overcoming several energy barriers. So, when you plot this as a function of distance, and that is why these processes are diffusional in nature, or they follow Arrhenius kind of relaxation. So, here suppose you can plot this as, you can have scenarios like and so on and so forth. So, you might have transition, for example, from this state to this state, you might have transition from this state to this state, you might have transition from this state to this state, depending upon the type of solid, whether you have a glassy solid, whether you have a crystalline solid. In crystalline solid there will be more ordered movements, in glassy solid there will be more disordered movements, but nevertheless it goes from one stable position to, or one metastable position to another metastable position. These are all metastable positions, right, in the free energy landscape. So, as a result, for a species to change its configuration from, let us say, 1 to 2, this is 1, let us say this is 2, they have to overcome a energy barrier. So, this is energy barrier which has to be overcome. So, when they go from 1 to 2, they cross this energy barrier, then 2 to 3 again there is an energy barrier, then 3 to 4 again there is an energy barrier. So, as a result there is a considerable slowness as compared to the previous, because everything is, it has to diffuse from one place to another to another. Diffusion is basically Arrhenius phenomena. So, when the diffusion, so if you look at the lattice for example, so when this atom moves from this place to another, this place, so basically it undergoes energy barrier, because the transitions that take place in the middle, they dilate the lattice. As a result, there is a sort of temporary generation of strain in the lattice, it has to overcome. So, it has to break one bond, form another bond. As a result, there is a activation energy, you can say Q, that is needed for transition to occur. Similarly, in this fashion it has to go from one position to another. As a result, the process is sort of diffusional in nature, requiring an activation energy barrier to be crossed. So, here let us say the case of ionic solids. So, considering cases of ionic solids. So, when you apply electric field, now you apply an electric field. Now, as compared to this relaxation, the frequency scale at which ionic and electronic polarization will develop will be very fast. So, basically when you apply an electric field, you will develop almost instantaneously you will develop a electronic and ionic polarization, right, because they are very fast. So, when you apply let us say a field of frequency 10 to the power 6 or 10 to the power 7 hertz, which is very fast as compared to 10 to the power 13 hertz, right. You can see that there is a magnitude of difference, 7 orders of magnitude difference. So, when you apply frequency electric field of this sort of frequency, then generation of electronic and ionic polarization will be almost immediate. So, when you now plot this polarization as a function of, so let us say I plot polarization as a function of time, then almost instantaneously I have a contribution from electronic ionic, let us say this is P electronic plus P ionic, and the saturation polarization then develops over a function of time. So, let us say this is the value of saturation polarization in a given system, the maximum value of polarization that you can get, and this thing takes its own time to develop. Eventually it does reach the value, but it takes time, and this is the dipolar polarization, which is time dependent polarization P d t. So, as compared to electronic and ionic part, this development is far more slower. Okay. So, molecules basically you can say this is a molecule in this fashion, this molecule has to now rotate to go to this position. Okay. So, this is what and this you apply electric field, it has to come to this direction, but it has to rotate, it has to undergo a rotation in the matrix or in the structure. So, correspondingly if we assume this model to be true, then we can, so rate of change of polarization can be so we write the rate of change of polarization as dP by dt is equal to 1 over tau Ps minus P d t. So, where 1 over tau is basically a proportionality constant, and this equation is called as relaxation or basically it will come to be as time constant tau, okay, which is proportionality constant. So, this is basically, this model is sort of called as bistable model, where you go from one stable state to another stable state. So, basically this change in polarization Ps minus Pd, right. So, essentially you are looking at the rate of change of polarization within this regime, and at any given time the polarization is Pdt, and when you reach here, then of course at very large times when Pd is equal to Ps, then rate of change is equal to 0, right, the slope is equal to 0. So, that is what it represents, dP by dt is equal to 1 over tau into Ps minus Pd t. So, now, so we call this model as bistable model. Okay. So, basically what we are saying is that you have a charged dipole like this, whose orientation was like this, and now this charged dipole changes its orientation and the orientation changes. So, this is position 1, this is position 2. Okay. So, let us say if I make it little colored just for the sake of illustration. And this is where you apply electric field. Okay. So, essentially we are considering, so energy landscape can be plotted as, let us say this is position 1, this is some position 2. So, this is position 1, this is position 2, and it has to overcome an energy barrier. So, if you look at from this side, the energy barrier will be this EA, and if you look at from this side, the energy barrier would be this much, and this distance between the two is equal to, let us say, delta. Okay, this is the distance between the two positions. Okay, so, this is position 1 corresponding to that, position 2 corresponding to this. So, this is position 2, this is position 1. So, when you apply electric field to such a polar material, then ions hop from one position to another position. So, this could be, for example, in glasses you have silver ion conductors, sodium ion conductors, etc. It could be dielectrics, it could be ice structure or water molecules. Various materials which are polar in nature will show similar kind of behavior. So, as you see, so we can see in the previous image that cations are, so let us say it is related to cations. So, cations are moving from or let us say, instead of saying cations, let us just say species, okay, because it could be anything. So, species are moving from left to right, okay, and temperature is greater than 0 K. This is what we have to first see. So, as a result, there is a so when the temperature is greater than 0 K, which means there is a random oscillation also, right. Random oscillation of species between, because when your temperature is greater than 0 degree centigrade, the atoms or molecules will vibrate. As a result, there will be equal probability, there will be a probability of rightward movement, there is a probability of leftward movement as well, which is basically true for any solid. So, now let us calculate what is the probability of jump between the sites. So, when we look at the probability of jump between the sites, let us define this as f. We could have written as p, but p is something that we have defined for polarization. So, let us not confuse. So, let us say this is a into exponential of minus EA divided by KB T. So, this a is something here that we will see later on, but let us say for now the a is some sort of constant, okay, and EA is the activation energy or the barrier which species have to overcome to move from one position to another. K is the Boltzmann constant, T is the temperature, and A is some D exponential factor. So, when you apply electric field, so this is symmetric. Let us say you have a situation like this where the wells are symmetric, okay. So, on both sides the energy barrier will be similar. So, this is symmetric to begin with, and from when you go from 1 to 2 or 2 to 1, they have to face the similar EA, okay. So, as a result, you can see if you go from 2 to 1 or 1 to 2, the probability will be same. Now, when you apply electric field, so electric field will be in certain direction. As a result, the wells will tilt, right. So, you might have a situation like this, or you might have a situation like this, right. So, you can see that there is a asymmetry in the energy barrier. So, when you look at situations like this, you can see for atoms to hop from this side to this side, the energy barrier is lower, whereas from 2 to 1 the energy barrier is larger. Now, in the converse case, the hopping from 1 to 2 is more difficult, but 2 to 1 is easier because the energy barriers are now. So, basically application of electric field basically leads to tilting of energy wells, leaving asymmetry in activation energy barriers. So, when depending upon 1 to 2 and 2 to 1, when the magnitude of EA has changed, which means the probability also has changed. So, which means F1 to 2 will not be the same as F2 to 1. So, in this case, when it is symmetric, then F12 is equal to F21, right. The probability of when there is no field, it is same probability, that is why you do not see overall diffusion. But here, now that you have applied a force, which is let us say electric force in this case, electrical force, then F12 is not equal to F21, there is a asymmetry in EA magnitude. As a result, EA 1 to 2 is not equal to EA 2 to 1, and this leads to asymmetry in the probability of jump. As a result, you will have a net flow of dipoles, right, net flow of species from one to another. So, let us say we calculate this F12 is equal to 1 minus mu E divided by kT. So, initial was F12 was equal to this and F21 was equal to 1 minus. So, this, so one of them will be plus, one of them another would be minus, and let us say, so this would be 1 plus kT. Okay. So, on one side you have added the energy, on the other side you have subtracted the energy. So, this is what we will take it further. So, we have run out of time now. So, I will just summarize what we have done is we have just taken the simple bistable relaxation model, where we are saying that when you apply electric field of certain frequencies, the dipoles move from one position to another position. This is basically at lower frequencies. So, when you apply such a low frequencies, the electronic and ionic polarization will develop almost instantaneously, but the dipolar polarization will be time dependent polarization, and this will happen on a much longer time scale. So, as a result, and why this happens is because you have a species moving from one position to another position, and there is a and this process is called as a relaxation, and they have to overcome an energy barrier. And since they are moving from one place to another place, there is a possibility of movement, back movement as well, because the process is diffusional. So, we need to calculate the probabilities of movement from one side to another, from one to another, and so 1 to 2 and 2 to 1, and we have to calculate the net flow of dipoles from 1 to 2 and 2 to 1. So, this is where we are right now. We will look at this a little later when we in the next lecture. Okay. So, thank you very much.